All right, welcome everyone to today's webinar on materials at extremes, sponsored by the Chicago DOE Alliance Center here at the University of Illinois, Chicago. Today I have the pleasure of introducing a longtime colleague and friend, Xiaojia Chen from the University of Houston and the Texas Center for Superconductivity. Xiaojia is a well-known and highly productive experimental condensed matter physicist who's made a lot of important contributions to the study of quantum phenomena, including superconductivity at high pressure. Xiaojia obtained his PhD in condensed matter physics from Zhejiang University in China. He was a postdoc there in China and then moved to the Max Planck Institute, was for a while a research associate at Kent State University. And I think it was sometime in the early 2000s, we met at a Gordon conference, and I convinced him to come to Carnegie to join our group. And he joined our group in 2003, stayed for some 10 years, contributing to a lot of projects, including work in our Energy Frontier Research Center, working on superconductivity, on nitrides, hydrides, and cuprates. And one of his, I think, really notable contributions was an important paper in Nature published in 2010 on the non-monotonic behavior of the TC of BISCO under pressure, one that's been, I think, highly influential. In 2014, he joined HB Star in China. In 2019, he obtained a chaired professorship at Harbin Institute for Technology. And last June, he returned to the States to the University of Houston, and he is now the MD Anderson Chair of Physics. So we're looking forward to your talk and this exciting future directions in the study of superconductivity and hydride, something we're all quite interested in. Over to you.
Yeah, thanks for the introduction. It's really my great pleasure to be here. I saw a lot of audience from early colleague friends. Also, I invited Professor Hirsch from UCSD. Also, I saw like James Schilling, my long term is supporting from him. I feel, it's a great honor to be here. Today, I mainly talk about, work we have done in the past few years on hydrides or light element containing material like carbon or carbon hydrides, like organic system. The talk will, showing this indeed is a promising direction for exploring high tissue conductivity.
Like no, wow.
So here I would like to show my collaborator for this work, experiment for synthesize, measurement, and data analysis from a former employer is HP Star. Also, a point context spectroscopy from a collaborator in Korea. Also, a Lansom H10 sample got from Zhulu and Ras. It's Victor brought to us. And also theoretical supporting from my collaborator, Hai Qinglin and Zhonghua Guo, that's from China. As well known, superconductivity is a very important quantum phenomenon after liquefied helium in the last century. From that, the superconductivity phenomena was showing is extremely important. To characterize this phenomena, we'll need to determine that zero resistivity, also perfect diamagnetism, that's a Meissner effect. Since this phenomenon is so important, there's a 5-time Nobel Prize award to the superconductivity related works. That's 1913, 1972 for the BCS theory, or Josephson, also to Alex Mueller and George Bednaus for this kind of Kuiper's superconductor. Later in 2000, sorry, I don't know how come. Okay. This also, as I mentioned, there are at least two more Nobel Prize for superconductor remains. One is macroscopic theory for high-T superconductor in Kuiper. Another is for the room temperature superconductor. Also, potential new applications of superconductivity. There's three topics. It's a field, at least there's two more Nobel Prize for superconductivity. Since the discovery that technology application already is going on in many places, including US. There is here, New York, Long Island, also MacLab in Shanghai, China. MRI is almost everywhere in major hospitals. I also would like to mention, since for the clean, economic, and efficient energy application based on the superconductor will come soon. You can see from ITER and also Saparic in Denver, Massachusetts. They are building the machine that will deliver electric very soon. Plan plasma in 2026, fusion energy in 2027. If that be available, almost each community, you will have the fueling station. The electric will be cheaper, it will supply is constant. This cost, is a little bit cost. Volume substantially reduced, and compared to ITER. This adventure is based on the achievement of using WBCO or other kind of based on 103 Kuiper superconductor as a magnet, because this magnet has a field strength up to 20 Tesla. That's why the size can be substantially reduced. And there's a possibility if transition temperature is higher, you will have a much higher upper magnetic field. Then the fuel machine will substantially reduced. This is a fueling, will bring a real golden age for the application of superconductivity. These are big expectations. Since we are so interested in getting a high transition temperature, where can we find it? Actually, from Neil Ashcraft, their early paper is metallic hydride, is a pole for high T superconductivity. And also in 2014, Ashcraft mentioned there's a hydrogen dominant metallic alloy also serve a pole for high TC superconductors. Particularly mentions group 4 hydrides like methane, selene, germanium also. In 2003, Nobel lecture from Will Ginsburg, he listed 20 that's a physical minimum at the beginning of 21st century. You can see the first one is controlled nuclear fusion. As I said, that will give a substantial energy in future energy revolution. Now, Kuiper superconductor already used as a magnet to generate magnet. with a high upper magnetic field subtly reduce the size of the fusion machine. And the second one rank is the high temperature, room temperature superconductivity. We'll see actually today in hydrides, we already reached the room temperature superconductivity. The third one rank here is metallic hydrogen or other substrates. We'll see here is a metallic hydrides serve the the kind of showing the metallic behavior similar like a metallic hydrogen. In hydrogen, you can see based on calculation and like 200 GP is an early work from 2001, published from Solid State Communication. You can see the calculation will give you at high pressure, TC can be here like 600 Kelvin in metallic hydrogen. Also, in the other kind of calculation, you can see at CMC phase, that hydrogen will have TC around 250 Kelvin. Here is the more reliable calculations. There's a phase transformation from molecule to atomic phase at a very high pressure. You can see as a molecule is space groups CMC, but in atomic phase, I41 AMD. The calculation also showing you that in either molecule phase and atomic phase, TC pretty high, really very high, like above 500 Kelvin. However, this is really hard to get a metallic state. That's why in 2004, Professor Neil Ashcraft had a proposal that's borrowed from an idea from MGB2. That's a group of 4 hydrides probably will hold a possibility to exhibit a high TC superconductivity. Since then, we work on that. You can see from the photo of the group, Russ is there, and Zhen Xian, and also Alex Goncharov, and Mokhtar now in Illinois. That's Victor and me. We published paper, is first experiment regarding the selling. We reported the high pressure phase transformation, also the possible metallic state. Even there's somebody argue this, this probably dissociation or other kind of issues. However, when we have a calculation, we can see the TC at high pressure not that high. There's a 150 GP, there's a TC around 20 Kelvin in this system. Actually, from Michael's work, they published later that year in Science, they indeed report that a TC around 17 Kelvin in that system, that's such pressure. Also, we work on German. You can see the phase transformation in this system. We can see systematic change either from Raman and from infrared spectrum. At that time, we saw there's a dissociation of selenium, germanium, and high pressure. If it's happened, that's a germanium. We are in the hydrogen environment. That's why we mentioned germanium will surrounding in the very good hydrostatic pressure media. That's why we investigate the structure in changes and pressure. Then at that time, the structure changing as a evolution for germanium not well defined. we use the idea for that. We establish the equation of state and the structure evolution of germanium with pressure. That work published in 2011. Here, I would like to mention the great breakthrough came from the chairman, his group. That's Zulu is the first leading author for that paper they published in 2019. It's a PIL paper. For that paper, also work from Michael Ermert. You can see really is TC from resistivity measurement showing at around 200 GP. The TC drop and reach the zero resistance state above 260 Kelvin in both measurement. Now, the room temperature superconductivity comes. That's from the real earth element hydrides. This is a real case. But it's taken many years. We will add this new material in this superconducting family. That's near room temperature superconductivity. That's why this the history will be changing. We will rewrite this transition temperature with the years. Their discovery actually based on the brilliant idea. They synthesize material use like ammonia boron. That's NH3, BH3. When you use laser heating, this will deposit 3 hydrogen, also give you cubic baronitride. Cubic baronitride was often used to put electrical leads holding like gasket holes, like here, like B in this figure A. That's a baronitride. When you heat this ammonium boron, it's generate hydrogen. Meanwhile, give you a supporting cubic baronitride. It's so important. That's why the size is due to the choice of these the hydrogen sources. Also, they calculate this TC is almost the same to their measurement. It's a near room temperature superconductor is created. This superconductor is interesting because you can see that the cage structure. That's why the real Earth can holding a lot of hydrogen atoms. That's accelerator structures. This structure from you can see that's early work 2018. The ZEC already defined this structure. That's LAH10. Following their discussion, their issue always need to be addressed. Is this really a superconductivity phenomenon or not? As I mentioned, the superconductivity will need 2 characters. One is a realize of zero resistance. Another is a Meissner effect. Last year, almost is February 28 this year, is a group from UC Berkeley and Harvard, just from Yale's group. They collaborated with Tian Cui from China. Also, a lot of our colleagues, you can ZEG, also Victor is a course here. They use AV diamond. They showing, you can see when entering a superconducting state, that's showing that's a Meissner effect. It's showing here, that's a right side. Now, that's an issue for superconductivity already pinned down. The superconductivity in hydrogen is real. Following their design for synthesized material, we also work in this field. Later, we choose NH3, BH3 as hydrogen sources. You can see we are thinking to reduce the synthesized pressure because in the early measurement, you can see the pressure pretty high, above 200 GP or near 300 GP. We're thinking whether we can lower the synthesized pressure. Meanwhile, we can maintain at a high transition temperature. We choose selenium to dope like yttrium or lanthanum. As a try, we put alloy with a component like a 1/1. Here is Y, like C, the 1/1. You can see we synthesize, use a procedure Julo and Ross they used. We put it's AB, like NH3, BH3 as a source, hydrogen sources. Here, we would like mention that's a fingerprint we found is a peak at a low frequency. Like you can see here the right side hand, you can around 170 wave number. We mark a star. We mark the star. Actually, that's a fingerprint for hydrogens. We'll see that. Also, you can see when you use a laser to hit a sample, you generate the hydrogen. Hydrogen, we can see Raman like around 4,000 wave number. You see clear hydrogen peak. Also, we see some feature from hydrogen S1, S0 mode here. Our Raman, the low frequency mode, is coming from its hybrids is based on the calculation. You can see the upper, we have two calculations. That's a phonon dispersion. It's a gamma point. You can see like 200 wave number in both compounds. That is a feature we observed here. Here, I show you is lanthanum and selenium 1/1 ratio of hybrids. You can see that's figure B. We mark a star. All these stars indicate the sample already created. That's hydrides. That's hydrides. That's a fingerprint for hydrides besides hydrogen. Here is the in situ measurement. We put our synthesized cell, diamond cell in corrector, low temperature corrector. Then we can get Raman and resistivity at the same time. You can see the measurement showing you resistivity in warming run, cooling run. In both run, resistivity drops significantly, and zero resistivity already received. You can see the onset for this sample is 175 Kelvin. For another sample, we synthesize material in the same procedure. You can see we mark the star in the figure B. Also not showing so clear. The resistivity measurement showing you the transition like 131 Kelvin. We use X-ray diffraction to determine the phase. You can see that X-ray give you a feature for the peaks that belong to this like a space group like FM -3M. That's a cubic phase for our lanthanum selenium H10. For that's yttrium like selenium, H9, we also have the diffraction. Diffraction gives you that as a cage feature as well. Here we show for the resistivity measurement with the magnetic field. You can see when you apply the magnetic field, the resistance is suppressed, thus the transition getting wider, and we can determine the applied field here. Now, since we already determined the TC, you can see we plot here to compare all the previous published data for lanthanum H10 or yttrium H9. You see the introduction of lithium, selenium in lanthanum H10 and Y H9. Clearly, the TC is remains pretty high, but the pressure substantially reduced. This is two work we published last year. In order to determine superconductivity application, you will need to determine critical temperature, critical field, also current, the critical current. Here we give you an example, and we publish for potassium carbon 60. You can see we determine upward field that pretty high magnetic field up to 60 Tesla. And we measure the magnetization versus the applied field to determine the current for this. As I mentioned, there's a hydrate measurement still need to make an effort to establish all these parameters. We work in the way to determine that superconductivity gap. Here is the example. This sample we received from Julo and Ross. We take the measurement, the Raman measurement as a function of temperature, from room temperature to the temperature like a lowest like 180 Kelvin. You can see for each 10 Kelvin we collect a scan spectrum. We subtract, you see that's the spectrum in the superconducting state and the normal state. You can see we clearly observe a gap opening around 1,600 wave number. From this wave number, we can determine the ratio of 2 delta divided by BTC. That gives you 8.8. That means that's a strong coupling interaction superconductor. That's why TC is pretty high, so high. But in cuprates also there is around 10 also was reported as well. Compared with BCS, the ratio is 3.353. We also use point contact spectroscopy. That's from my student Ziyu Cao in collaboration with a group in Korea. You can see we determine that from normal state to the temperature down to 2 Kelvin. Then we have the gap function changing with the temperature. From that, you can determine to delta 0 BTC. That's pretty low compared with our lanthanum H10. That's a little bit low. Since we determine the upward field, the coherent lines can be determined. It's pretty also very low, like around 20 to 25 astro. From that, we can determine the Fermi velocity. Fermi velocity for selenium H9 is 3.35 times 5 meter per second. That's why we can determine flame temperature for this material as well. When we put in here, you will feel it's really surprised because you can see it's here that TF is pretty high. It's sitting close the bismuth 2223. It's close to the BC line. It's a short region pair. It's a short region pair. That's an unconventional feature for superconductivity in hydrates. And following this way, we also thinking, in the cage for the hydride. We borrow this idea also in light element. Light element is carbon. It's a carbon cage network. We choose like a kind of lot of system. We found that TC even at ambient pressure can hold in transition temperature above 100 Kelvin. That's in carbon cage. Also is a light element. Here is a boronitride. It's a BN4. When you form a compound with hydrogen, we call hydrogen the boro 4 N4. This material also have a TC around 120 Kelvin at ambient pressure. Very recently, like a few days ago, one of a paper accepted by PRB. In this paper, we have just two elements, hydrogen and carbon. You can see hydrogen, carbon 6. That's a TC above like 100 Kelvin. This actually realized at ambient pressure. Very recently, you see yesterday, the Nature News mentioned that unconventional superconductor excited physics. Why? Because in the nucleus, there's showing you on set temperature like 45 Kelvin. You can see here, and the zero resistivity state reached below 10 K. Also, they give AC susceptibility measurement. I think this is a susceptibility measurement showing you the transition below 9 Kelvin. That's this material was reported to exhibit superconductivity at high pressure. But now its ambient pressure superconductivity is reached. That's why we mentioned for our hydrides, it's room temperature transition. We probably can borrow some idea to have a new form of our phase. It's superconductivity showing the transition near room temperature is possible. You can see the work done for this is length of nickel oxygen. They early report 2023. They didn't reach a zero resisted state. You can see the left column B. That's have a residual resistance. You even cannot declare that is a phenomenon of superconductivity. That's why they use a title signature of superconductivity. Also for the figure C, they mention there's some kink from the susceptibility. That also cannot use as a signature or evidence supporting the realize of superconductivity. That's why at that time, even they published in Nature, but this work cannot, consider as evidence to supporting the realized superconductivity. Later, a group from China published one paper for this material. Indeed, they reached a zero resisted state you can see the inside of a red panel, they showing you there the resistive state has been reached, but TC is not so high. And that's why, as I mentioned, this idea is a modification for the superconducting phase in some kinds can give you the possibility to holding your high TC superconductivity. In the hydrides also, this idea should be borrowed. Also, there's a work from Stanford University. You see, they use the title as a signature of ambient pressure superconductivity, the length of nickel oxide. You can see from all their figures, it's really hard to find this, this evidence supporting the superconductivity. But now, since the work from this film indeed showing you the evidence, this is why that's Nature Physics give you a title, the Excellence Physics. This idea actually is not new. You can see that CS3 carbon 16 fluoride, this superconductivity was reported to expand at high pressure, not so high, so around 5 kilobar or around 1 GP. And we made effort to reach that's room time, that's ambient condition, ambient pressure. We have a superconducting phase. Here I show the detail of the structure and the X-ray diffraction. Also showing you the measurement from this DC measurement and the AC measurement. Clearly, magnetization shows a law for this, and the resistivity shows a clearly realize of zero resistivity state is 18 Kelvin for this. That's why it's some kind of modification for the phases really can help to maintain the high pressure phase of all the features, but that modification happened at ambient pressure. The carbon 60 was, discovered in last centuries, and the paper publishing in Nature in 1985. The Nobel Prize was awarded for them in 1996. You can see later there's a work from Bayer Lab reported the evidence showing to support superconductivity at 18 Kelvin in potential doped carbon 60. At that time, I would like to mention their measurement was not done on same material. The resistivity, they use the film. They use the film, but the susceptibility they measure for bulk material. This is the measurement for supporting the two characters of superconductivity from two samples. We are the only group in the world to reach two characters supporting superconductivity from same material. Here I show the example for we published 3 years ago for the potential doped carbon 60. That's ZFC from DC measurement. The real part of susceptibility, imaginary part of susceptibility clearly show the peak. Also resistive, that's from same samples. That's the first time in history, the carbon 60 showing there's two characters for supporting superconductivity. We work in the field that's carbon as RB or CS, and we measure resistivity. We have the TC measurement, and also we receive the structure with the pressure. That's why we got the TC changes with the lattice parameter. You can see in the three systems, the carbon 60, that's K3, RB3, CS3. If we put them together, we get the figure in red panel. Carbon is not one example for organic system. Actually, in the conducting polymer was discovered also last century, almost at 10 years early. 10 years earlier than cuprate. You can see here that conductivity substantially increased in polymers. And so far, there are a lot of conducting polymers. We mentioned their possibility to exhibit high T superconductivity. We worked on that in the past 10 years, but didn't accepted by community. Probably community has some special requirement. And also for these material kind of polymers, the transport quasi-particle not finalized is still remains is a soliton or bipolaron or polaron. In a few years, we work on this in the potential doubt that 3 benzenes ring. You can see we have the FC measurement, and it's a low field. You see there's a transition above 125 Kelvin. That's in ambient condition, zero pressure. You can see here the only element is lighter element is carbon and hydrides. And also similar to that we discovered in hydrides. When we take the measurement, I enlarge the figure here. You can see the magnetization versus the magnetic field. You can see that a diamond shape is here. That indicates we indeed reach the Meissner effect in this system, but this happens in ambient pressure. We are working on this system. There's a lot of groups in the world. They are so interesting to this discovery. You see from this university, that's from which university? The group here, they use the spectroscopy measurement, showing when entering the superconducting state, clearly you observe the conducting gaps opening. Also, the group in China, they observe this, and the India, they also showing the susceptibility split and the diamond shapes here. All these supporting Meissner effects already reached in this system, but this happened for the system at ambient condition. Now, I would like to mention the conclusion. Indeed, TC can be higher. A lot of material can be discovered. The mechanism can be getting clear. The application for fusions is comes. Thank you for your attention, for your time. I would like to pick up questions.
Thank you, Xiaoxiao. Thank you for that nice overview. Lots of great work. I'm sure there are questions and comments. Just raise your hand or unmute yourself or put them in the chat. Jorge, do you have a comment or question?
Yes, I have a question. Thank you, Russ. Thank you very much for a very interesting and full of content talk. I wanted in particular to ask you about, you showed a slide of, I think it's point tunneling, the IDV, and the you know which one I'm talking about?
Yes, I knew.
Yeah, so first of all, a paper is quoted there, but I haven't been able to find it. Is that paper available? A paper
We put
called,
online. We
is
put
it,
online. You
is it,
can
on- is it
you
online?
can easily get an archive. Yes.
It's on archive.
Yes.
Recently. Okay, and the shape of those curves didn't look to me like the usual DIDV. Can you comment on that?
Yeah, I understand. This you see that's a technique is a poor man's technique. Point
Okay.
contact spectroscopy, not that beautiful as other technique, so the tunneling for convention super element. But this is we developed this technique. This technique are already borrowed. You see in measuring, many kinds of material, including cobalt, iron, and lot. But at a pressure like above 100 GP, we give a signal like that is also is a big achievement.
I will look at the paper. Thank you very much.
Okay. Also for tunneling, I show you that's from electric Raman scattering measurement, give you the that's a surveillance gap as well.
Okay. Can you just tell me the date on archive roughly? When did you post this?
You can find the link. I think Russ already have the announcement with the link for that as well.
Thanks.
Great. More questions, comments? I'm seeing some of the data for the first time on some of these systems. For example, the sample that we prepared many years ago on lanthanum hydride, the electronic Raman is very interesting.
Yeah.
And the analysis shows that the gap you extract doesn't fit BCS, which is very, very interesting. And I understand that there are some data that are unpublished on H3S that also don't fit BCS. Are you aware of that? Have you thought more about why there's this difference?
It's following that, but they give you a ratio like for Lansum H10, that's 8.8. It's incorporate. This ratio can compare. There's a lot of corporates also around 10 or even 16. That's indicate the strong company.
Yeah, right. Okay, we should follow up on that. Thank you. Adam, do you have a question, comment?
Yeah, a very basic question. Because I don't know much about the fullerenes and doped fullerene compounds. When you make a bulk amount of it and are say looking at superconductivity, especially in your case, they're at ambient pressure, does do these fullerene compounds are they like a compressed powder or are they fully like a crystalline lattice?
That's a benefit for our high pressure community because we work on a high pressure field for a long time. We use the press to compress that powdered into pellet that measures resistivity. That's we follow this idea.
Gotcha.
That's why we can reach a zero resistive state. Otherwise, it's pretty hard. You guys check the early publications, really hard to get resistive development. That's
Yeah.
why I'm so proud to get that.
Yeah, I believe it. It's very interesting work. The follow-up question then is you would expect then if it's a compressed powder, basically a ton of like grain boundaries and whatnot. Does that affect like the phenomenology of the superconducting state? You know, could it be doing something unexpected in your measurements?
You see, now we already collect a lot of data, so use multiple techniques so far. So You see, but we don't know what else. But what else measurement we still need to do. But these are not sync crystal. It's powered. So that's probably we are still working on that.
Great. Thanks.
Thanks, Adam. I believe Warren was next.
Yes, maybe a brief question. The last topic you mentioned was TC, I think, TC greater than 100 Kelvin in potassium doped P-terphenyl. Is this published work somewhere? Is it recent?
Now, we post 3 papers online in 2017, and since that's not accepted anywhere, we submit PIL. PIL mentioned if you have the data, we will need the strong evidence to support that. We are still working on that. You can get this online soon.
So that's unpublished work.
Unpublished work.
Thank you.
Unpublished work. But people, they published this published work. These are published work.
Okay.
They observe similar thing. I didn't show the resistivity measurement. There's a work from Italy. There's many groups, they work together. They sense the material, measure resistivity for this material. At the same temperature, 120 Kelvin, they indeed observe the resistivity drops substantially, 3 orders. They publish their work.
I believe Christoph was next.
Yes, thank you very much. Thank you very much for this excellent overview of superconductivity. A really great lecture. I think that it should be possible to get experimental structures of the most of the systems. You are using powders. In powders you have crystallites of size close to micron. These days you can collect really single crystal high pressure data separately from each grain. And that should give good data sample from synchrotron measurements, and when they refined with modern methods, this quantum crystallographic methods, they should give us, in my opinion, structures of these hydrates and other systems, purely from experiment, not from computations. Have you tried this kind of new approaches or not?
That's a really great idea. I totally agree with you. Last year, I went to, France. There's the synchrotron, beamline. I saw if it's a tiny sample, they can use their facility to get synchrist peaks. They can refine that, get synchrist structures. We think that's a good idea. We will do that in future. You can see here, that's a sample. The sample actually, you can pick up the area with the crystal, even the tiny, but it must be micron size. That's enough for collecting.
Yeah, that's definitely enough for several stations. ID27 at ESRF would be ideal, and I'm sure that also at APS, after this upgrade, it should be possible to get such data. And I will be more than happy to refine them with using this quantum crystallographic methods.
Thank you so much. You see here, this X-ray spectrum is raw data. I show you here the raw data. We refine, that's a raw data. We didn't, subtract anything. That's a raw data. That's a raw data.
Yeah.
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 Yeah. You can see the sample size like this. I think definitely you can pick up the micron size synchrist to get spectral refined synthesis is accurate structure.
Is in those systems, is superconductivity somehow related to a given direction? I mean, you are showing mostly cubic structures, but even in cubic system, in the direction 111, you have different properties than in 110 or 100. So how superconductivity behaves as a function of direction is anisotropic or isotropic in the crystal?
It's hard to tell from the data like that. Probably that will be a issue will need to be addressed in future.
Thank you very much.
Yes, thank you.
Yeah, that's quite difficult to determine at very high pressures where you have a lot of mixed orientations of grains. Let's move on to Anmol.
Hi, very nice talk. Thank you. I have a question again about the your measurement of the gap value for lanthanum hydride with Raman. So you said so. If I understood correctly, you're comparing the gap value of 8.8 and then like the calculated ECS value, and so because it departs from that. You're saying, yeah, it's departing. So are there other evidences, for example, like from Raman, one could also get the electron phonon coupling value. For example, it was done for MGB2 or like, the different modes for particular modes too, like the electron phonon coupling value. I was wondering if you have done similar analysis for this system.
I don't know how to answer your question. Here, I will show you the phonon dispersion for this material at almost the same pressure. You can see that all these phonon feature, but from that, you can subtract electron phonon coupling interaction. But the Raman data we got is pretty hard to subtract. That's why we just got a feature. But
I see.
yeah.
I see. Okay. Good. Thank you.
Thank you.
Well, you can see departures from BCS from any measurement of the gap, right? From Raman or infrared or tunneling spectroscopies. So it's not just unique to Raman.
Yeah. Raman really is a very convenient, powerful technique. Very good.
Was there another question? Jorge, did you have one?
No, I'm good. Thank you.
Okay, any more questions, comments? If not, thank you, Xiaojia, for a very nice talk. Lots of great work over the years, and thank you for the review.
Thank all of you. Thank you all of you for your time, attention, and energy. Yeah.
Great to have you back in the States. In touch.
Yeah, really my great pleasure. To meet all of you here, and
Okay, bye-bye. Thank you, everyone.
Bye-bye. Take care. Bye-bye.